So from our discussion above, we've said that when dealing with ladder problems, that is solving questions concerning bodies in equilibrium, it is always better that you first of all begin by drawing a complete force diagram. In other words, drawing a diagram that is having all the forces acting on the system. Otherwise, in case anyone is missing, then we shall be having issues. So, having read through the question, let's try to draw a force diagram and we see how it looks like. So we have a vertical wall and we have a beam which is labeled AB, and according to the question they're saying that end A is hinged to the wall and end B is the extreme end there. So if it is a uniform beam, it means that its weight acts in the middle. The center of gravity is in the middle, meaning that if it is of mass 4 kilograms, then its weight must be 4g. So the 4g acts in the middle there. That is its weight. So if I assume this one to be our length L, then this other one should also be our length L as well. So at the same time, they're saying that it is there's a wire. The beam is held horizontal by a wire joining B to point C. So our point C is vertically above point A, and we shall call this one our point C like that. A stone of mass 10 kilograms is hinged at B. That means that at this point B here we have a mass which is 10 kilograms, meaning that its weight is 10g. And the angle ABC is 30 degrees. So this angle here is 30 degrees here. So in the string, we have our tension T. Remember, I said that in case the beam is hinged to the wall, then as a result, the wall also exerts a reaction onto that beam there. So that reaction is not the normal reaction, but a reaction at an angle. I'll call this one my reaction R. So these are the forces acting on our system. Now, after doing this, we said that we followed the rules, we followed the conditions for a body to be in mechanical equilibrium. And the first one is that the resultant force is always equal to 0. And then the resultant moment at point is also always equal to 0. So beginning with the resultant force, let's consider vertical forces first of all. Now, since this one is at an angle 30 degrees, I'm going to assume that its component vertical, I'm going to give it a letter Ty, but this Ty is the same as T sine of theta, as we saw in the slides up there. Then its horizontal component, I'll give it Tx, and this Tx here is the same as T cos of theta. And remember that our angle theta is equal to 30 degrees. Likewise, the normal reaction, the reaction at point A, I'll give that component vertical, I'll call it Ry, and then horizontal, I'll call it Rx. So, for the resultant force being equal to 0, vertically, the sum of forces acting upwards, Ry plus Ty, must be equal to the sum of the forces acting downwards, 4g plus 10g, implying that our Ry plus Ty must be giving us 14g. I'll call this one my equation 1. And then horizontally, some of the forces acting to the right, that is Rx, must be equal to some of the forces acting to the left, that is Tx. I'll call this one my equation 2. So the first condition has been verified like that the resultant force must be equal to 0. Then we also said that we take moments about a point, and the resultant moment about a point is always equal to 0. Now on this we said that we always assume, or we always take the moments at a point where we have very many unknown forces. So if this angle R, if this reaction R is acting at an angle alpha, we don't know what alpha is, we don't know what R is, so it is better to take moments about point A. So, following that, taking moments about point A, we shall say that this 4G at this point A is giving us the clockwise moment. 10G at about point A is giving us the clockwise moments. Then Ty at about point A is giving us the anti-clockwise moments. Tx is passing through point A. Rx is passing through point A. And then Ry is also passing through point A, meaning that all of those ones give us 0 moment. So sum of clockwise moments will have 4G times the perpendicular distance, which is L, plus 10G times the perpendicular distance from the pivot, which is 2L. This one must be equal to the sum of the anti-clockwise moments, which is Ty times the perpendicular distance, which is 2L. So simplifying this expression is going to give us excuse me, is going to give us Ty being equal to 12G. It's going to give us 12G, and that is our equation 3. Recall that our Ty is the same as T sine of 30, which is the same as 12 times 9.81, implying that our tension T will be equal to 235.44 newtons. Please, you can pause the video and check this one out. So after having got that tension T in the string, then we have to get our reaction R. Remember that from equation 2, from this equation here, we said that Rx is equal to Tx, and this Tx is the same as T cos of 30. So implying that our Rx is the same as T, which is 235.44 times cos of 30, and this will give us our expression as 203.9 newtons. Likewise, from equation 1, our Ry will be equal to, from this equation here, our Ry will be equal to 14G minus Ty, which is 12G, which will give us 2G, and this is the same as 2 times 9.81, which will give us 19.62 newtons. That is what we do get. So the task that we have here is find the normal reaction, the reaction R. From that triangle that you see there, this is our reaction R. This is its component horizontal, which is Rx, and then this is its component vertical, which is Ry. This is forming a right angled triangle, meaning that our reaction R is the same as Rx squared plus Ry squared under a root. When you substitute in your values, we shall find that our R is the same as 204.8 newtons. And its angle alpha, that angle alpha is the same as tan inverse of Ry vertical over Rx, which is the same as tan inverse of Ry, which is 19.62 out of 203.9, and the angle is 5.5 degrees. So with this, we have answered the question, which was saying that the force in the wire, that is the tension T, and we've got that tension T as 235.44 newtons, and then the force exerted by the beam on the hinge, and that is the reaction, which is 204.9 or 0.8 newtons, and its angle is 5.5 degrees to the horizontal.